So we constructed the tensor product and we looked at the functoriality of the tensor product. Now there's something that we can usually say about tensor products that is important. So let me recall that if M was a right R module and N was a left R module, we defined the tensor product and the resulting object was only a Z module in general. Okay, but it turns out that the tensor product often has additional structure more than just being an abelian group. There's often more we can say about it. Okay, and that usually comes when M and N have some additional structure to them. Okay, so here's the point: if M or N or both have additional structure, then the tensor product inherits it. Okay, then M tensor N inherits it. Okay, so let's make this a little bit more precise. So to make this precise, I will introduce something in maybe in great generality, and then we look at various special cases of this. Okay, so this is the notion of bimodules. So we have looked at modules so far, which is, well, it's an abelian group with an action of a ring on it. Now a bimodule is the following: you need two rings, let R and S be rings. An RS bimodule. Okay, so an RS bimodule K is the following: is an abelian group. Okay, and we will denote the structure. So an RS bimodule is an abelian group. So I'm calling the operation as plus with, well, it's got the following structures. It's a left R module, it's a right S module with a left R module structure, and a right R module structure, a right S module structure, right S module structure. Okay, such that, so there is an additional compatibility condition we require between these two structures, such that the following is true. So what does it mean to say there's a left R module and a right S module structure? Given an element M in your in K, what I can do is I can define, maybe I'll call it X. So given an element X in K, I can define left multiplication by a scalar from R, right? So this element makes sense because I have a left R module structure. But I take this element and then I right multiply it with an element from S, okay, which again I can do because I assume my module K, I mean my set K had a right S module structure. So Rx right multiplied by S, I demand should be the same as first right multiply X by S and then left multiply by R. Okay, this should be true for all elements X in K, for all scalars R in R and S in S. Okay, so any such thing is called a bimodule. Okay, and we say it's RS bimodule because R is the left module structure and S gives you the right module structure. So here are some examples. Bimodules, by the way, are extremely common. They are, in many situations you actually have bimodules. So here is a example. If I take a ring R, not necessarily commutative, then recall we have already looked at this. Then so R, I claim, is an RR bimodule. Then R is an RR bimodule, meaning it's got a left R module structure, it's got a right R module structure such that the two structures are compatible. Okay, via what's the definition? So given an element X in R, I just define the left action by just multiplication, and given X and given an element, I'll call it S, but it's again in R, I again define this to be right multiplication by S. Okay, so this is for all RS. So claim is that the left multiplication makes R into a left R module, as you have seen before. The right multiplication makes R into a right R module. But the new thing to check here is that these two are compatible. So let's check that. So I take X, I first act R on the left and then S on the right. Well, what does that give me? It's Rx multiplied by S, but then that's just, Rx acted by S is just Rx times S. Whereas the other order, by the same token, is R multiplying XS. Okay, but observe these two are both equal because the multiplication is associative by associativity of the multiplication in the ring. Okay, so that's exactly what makes R into a bimodule over itself, because the multiplication is associative and therefore the left and the right R module structures are compatible. Okay, so this is the first example. Any ring is a bimodule over itself. Secondly, so any a left module, for example, so suppose M is a left R module, or similarly a right R module, you can actually think of it as a bimodule. Okay, so a left R module is nothing but a bimodule where the ring on the right I just take to be the integers. Okay, so I claim that if M is a left R module, then I can actually think of it as an RZ bimodule. Okay, so firstly, what does that require? I should be able to think of M as a left R module. That's already given. I need a right Z module structure. But remember, when I say that M is a module over R, I already know that M is an abelian group, right? And an abelian group is of course a Z module. Okay, so here Z being abelian, I don't care whether it's a left Z module or a right Z module. It's the same thing. Okay, so here's the definition. So how do I think of it as RZ bimodule? Via the following definitions. Given X in M, R multiplied by X is just the usual given. This is the given R module structure. Okay, and then how do you do right multiplication? Well, that's because it's, how do I right multiply by an integer, if you wish, X times N? Well, that's just, there's also a Z module structure already. It's just X plus X plus X N times. This is provided N is positive. So our usual definition, if N is negative, you just put minus of X plus X plus X so many times. This is mod N times. And if N is 0, then you just put a 0 there. So this is the usual definition by which we make something to a Z module. So it's the same definition. Now the claim is that these two structures are compatible. In other words, if I take X, I first left multiply and then right multiply by an integer, then it's the same as doing this. Okay, but then this is just the R module property itself. So let's just check this for, I'll just check it for N positive, the others are similar. So what's the left hand side? This is just Rx plus Rx plus Rx N times. Okay, now what's the right hand side? By definition, it's R acting on X plus X N times. Okay, but because of the left module axioms, when R acts on a sum of elements, there is distributivity. In other words, it just splits into so many terms. Okay, and therefore that's the same answer as this. Okay, so in fact this is a RZ bimodule. Okay, so I should also add, similarly, if I had a right module, so similarly we also have the following: if N is a right R module, so there's a right action of R, then you can still think of it as a n is a ZR bimodule. You can think of it as a bimodule by just making the left ring into just Z. Okay, so same definition here. Okay, good. So this is the second important example. Now here's the third example, which is that if R is commutative, and this is a very frequently occurring and very important example, if R is a commutative ring, then an R module, a left or right R module, so if M is an R module, okay, recall here left or right is the same, we don't need to worry. If M is an R module, then in fact you can also think of it as a bimodule, then M is an RR bimodule. Okay, how? Well, given an element x of M, you must define what left multiplication by R is. This you just define as whatever is given, because M is already an R module, so you can think of it as, let's say you think of it as a left R module. Okay, so this is the given action. Now how do you define right multiplication? Well, you still think of it as the same given action. Okay, this is also the given action, but now you act on the left in some sense. Now let's check compatibility. So if I do this Rx followed by S, well then by definition this is S acting on Rx, okay, which is by the action of by the axiom of the module, right? Because it's a R module, I know this axiom here. Similarly, if I first act XS, then by definition this is R acting on S acting on X. We just use the definition again, but again by the module axiom this is RS acting on X. Now the point is R is given to be commutative, so these two things are actually equal to each other. SR and RS themselves are equal to each other, so of course the final answers are equal to each other. Okay, so what we have shown is that if you have an R module, then in some sense, this SS, you can think of it as a left module or a right module. The given action itself makes it into both a left and a right module, but in fact the given action also makes it into a bimodule in this way. Okay, so this is again a useful and important special case which will keep occurring in many places. It's useful to think of it like this. Okay, and finally here's the another example which is not any of these cases. So suppose I take the set of all matrices, for example, I take the set of all M cross N matrices over some field, maybe let's even do over the complex numbers. Okay, take all complex M cross N matrices. Now you can make this into a bimodule as follows. On the left I take all M cross M matrices, and on the right I will take all N cross N matrices. Then K becomes an RS bimodule via more or less the following obvious thing. I take an element of R, of this ring R. So I take an element X from K. How do I define a left action? I just take R times X. This is now the product of matrices. Okay, now this I am defining for all X in K, R in R, S in S. Okay, so if X is from K, that means it's an M cross M matrix, and so when I multiply it by it's an M cross N matrix which I can multiply by an M cross M matrix, so it makes sense, and the answer is again M cross N. So that's my definition on the left, and on the right it's again matrix product, but now I take a product on the right that's again well defined, and again the answer is still in K. Okay, and observe that for the same reason, because you're multiplying on two different sides, whether you first left multiply and then right multiply or do it the other way around, the answer is the same, because matrix product is associative. Okay, so I can call it this. This is just product of matrices, matrix product is associative. So it's just the product of those three matrices, it doesn't matter which order I take. Okay, good. So these are all examples of bimodules.